Hello, greetings from Minnesota. I'd like to start by thanking Amber Hupp for inviting me to contribute to this session and to Pittcon for recognizing the importance of this session full of great ideas about how to adapt to online learning and teaching here during the pandemic and going forward. So I'm going to talk today about our work over the past decade or so to develop a web-based HPLC simulator. And so I'll briefly talk about the history of the development of this tool, its foundation, and some of the key features. I'll talk a little bit about some examples of how I've used the simulator with my courses and point to some resources for instructors that are interested in using the simulator so you don't have to start from scratch, and give a very quick sneak peek at some of the future development that we're working on actively now. So I'm at Gustavus Adolphus College, which is a private liberal arts residential institution. We have about 2,500 or so students here, and we graduate about 30 chemistry and biochemistry majors annually. Roughly thirds of the majors we see go on to some sort of health profession or to graduate school or other things. And we have quite a large number of students involved in research in the department in any given year. So the courses I teach primarily are relatively traditional quantitative analysis course, typically about 25 students, and an instrumental analysis course, usually about 8 students or so. And I work with a lot of students in my research lab as well. So those are some of the places that I use this simulator to interact with those types of students. So in terms of thinking about where it fits, I guess I think about my work with students as covering a continuum running from quantitative analysis through to research experience. And of course, we see that their independence grows as they move through these experiences. The HPLC simulator, I would say, I primarily use in my courses, but occasionally we also use it for some of our research activities. However, we certainly use Chrome Academy extensively in the instrumental course and in supporting research learning for research as well. And we also work on some other, I would say, higher end or more sophisticated tools for simulating different aspects of chromatography. And so I use these things, but also complement these tools with a couple of main books that I use for teaching liquid chromatography, especially, which are shown here. So the simulator really, as it stands now, really started life as an Excel spreadsheet in the 2000s. At that time, it was something that Peter Carr and I had worked on. And then in around the early 2010s, Paul Boswell, who was a graduate school classmate of mine, basically took the spreadsheet and turned it into a Java application, which at that time lived on HP or could be downloaded from hplcsimulator.org. Two things happened at that point. Paul left academia, and also the maintenance associated with keeping the Java application alive became really taxing. And so around about 2015, my research group took the idea and basically developed a web-based platform for the tool that is totally independent of Java, so we don't have to worry about those problems anymore. And our sort of principles all along have been that we wanted a tool that was relatively accurate and versatile yet easy to use. And so we wanted to be able to demonstrate things like giving students the possibility to explore a number of foundational concepts, such as looking at the pros and cons of isocratic and gradient elution, effective particle size, a very contemporary topic, effective particle size and resolution and required pressure, and things like the effective flow rate on analysis speed and resolution through concepts like Van Deemter equation and things like that. So I would say the sort of critical or core aspects are based on experimental measurements where possible. And so we've tried to incorporate sort of keep it real while also being careful to not make it too complex. So for example, the pressure readout in the simulator is based on experimental measurements of viscosity of mobile phase as a function of the mobile phase composition and temperature. So again, these are based on published data for methanol, acetonitrile, and water. And similarly, retention that the simulator reads out, retention times as a function of mobile phase composition and temperature, are all based on published experimental data fit to the linear solvent strength model of retention for reverse phase separation. So as it stands today, the simulator is only capable of simulating reverse phase separations. Other aspects are not quite as sophisticated. For example, we haven't done too much in detail in terms of looking at or incorporating the impact of injection effects on peak width and retention. We know it needs to be done there, certainly, and we can adapt to recent advances on those topics, but that's going to take time, of course. And I just want to point out that all of the sort of underlying concepts in terms of how the simulator works have been described in quite a lot of detail about 7 years ago in this article in the Journal of Chemical Education. So you can download that and read through exactly how it works if you would like to know the details. So now I just want to actually show the simulator working with 3 quick examples. The first being comparison of isocratic and gradient elution, the second being optimization of resolution by adjusting mobile phase and temperature, and the third one looking at the pressure resolution trade-off when changing particle size. So at this point, I will leave my PowerPoint here and transition to the simulator. So again, this, as far as we know, runs in all common browsers. And the first thing I'll say is that when you go to the main website, which is multidlc.org/HPLC Sim, when you follow that URL, it immediately takes you to the sort of current version of the simulator. So that version is 3.3.0 at the moment. So whenever we make changes on our side, whenever you follow the main URL, it will always take you to the active version. Having said that, if you develop an assignment based on a particular version, we give you the opportunity here in the What's New page to go back and use any version that's not the current version. So it's helpful to pay attention to what version you see indicated here in the upper right in terms of the version that you're actually using, so you can keep track of that. Okay, so as a first example, and if I just gave a quick tour here, so when you come in initially, we have these 5 main panels with the chromatogram display here and some peak information down here. So we give you this checklist to choose the compounds you want to use. In this window, you can choose your mobile phase, acetonitrile or methanol, and water, whether you're doing isocratic gradient or gradient elution. In the case of isocratic, you can choose the amount of organic modifier. In the chromatographic properties, you can do things like change the temperature, the injection volume, the flow rate, and so on. And it reads out a number of chromatographically interesting parameters like the pressure drop across the column, the plate number of the column, the reduced plate height, and so on. In the general properties, you can do things like control how many points are plotted in the chromatogram. It also reads out here the mobile phase viscosity and then analyte diffusion coefficient, things like that. And finally, in column properties, you can choose the column, its length, diameter, particle size, if you want to play with the porosity, and very importantly, the Van Meter parameters down here. And there's also some readouts like the total porosity of the column dead volume, and so on. So in this case, for this initial example, I've chosen a homologous series of alkylphenones ranging from acetophenone up to heptanophenone. And this is very nicely illustrates under isocratic conditions here what we call the general elution problem, which is that early on in isocratic separation, we have very narrow spacing between the peaks. And as we go out to the larger homologs, we have increased spacing between the peaks, which is wasted space effectively. And so we can compare this isocratic separation with a gradient one by switching this mode. And immediately, just looking at the initial parameters, here we see that the spacing between the peaks is more uniform, and we save a lot of time without sacrificing much in the way of resolution. So here we have a 5-minute separation. We go back to isocratic. This was about a 1-hour separation. So I think it's very nicely helps students understand the value of gradient elution. And of course, you can play around with the parameters here in terms of the gradient time and the gradient range, things like the gradient delay volume associated with the pump and things like this. Okay, in the second example here, I just picked out two compounds, benzonitrile and acetophenone. And here just what I want to show is that you can very nicely and quickly show students the impact of the mobile phase composition and temperature on selectivity. So here we have two nicely spaced peaks, but as we increase the amount of organic modifier, we see that actually the peaks come together because of change in selectivity. At this point, they actually coelute, and if we go through that composition, we come out the other side at a higher composition where they're actually separated again. So this is really supports a discussion of the impact of the linear solvent strength parameters S and KW on selectivity and how we can optimize separations by changing the mobile phase composition, in addition to optimizing separation time by changing the flow rate, for example. Likewise, similar thing can be done with temperature here. So here, this is what we get at 40 degrees. If I change the temperature, I can move them farther apart. If I go to lower temperature, I see that actually they will start to overlap. Okay, in the third example, what I wanted to show here is the impact of, first of all, flow rate. So these are the same two compounds I had before. The resolution here is about 2. If I increase the flow rate to 5 mils a minute, we see that the peaks broaden and we lose resolution because we're beyond the optimum velocity in the Van Deemter curve. So this allows us to demonstrate that to students. And the last thing I want to show here is the impact of particle size. So here I'm showing this separation is with 5 micron particles. If 5 micron particles in 26 bar of pressure. If I go to a 2 micron particle, now I have a better separation. The resolution is increased, but the pressure goes up dramatically, 160 bar. So this allows us again to talk with students about this compromise. When you try to optimize particle size, you have to consider pressure and you have to consider the resolution gain that you might achieve from that. Okay, now I'm going to go back to my presentation. So just a couple of examples of that actually are related to what I just showed with the simulator, and that is how we can think about using this in a homework assignment. So in this first example here, I asked the students to pick some compounds under a given set of conditions and then adjust the mobile phase composition until we have all of those compounds resolved. So again, this is along the lines of the idea that we can optimize the separation quality by changing the mobile phase composition. In the second example here, so practicing chromatographers carry around in their minds lots of rules of thumb. For the one that we're getting at here is that for every 10% change in acetonitrile in the mobile phase, the retention factor of a compound will change by about a factor of 2. So this asks the students to, let's say, collect some simulated data and develop their own rule of thumb based on what they see in the readout from the program. In the last example here, I asked the students to vary the flow rate from a relatively low flow rate to a relatively high flow rate. and record retention times, resolution, and peak height, and then ask them to rationalize those trends that they see based on the theory of peak broadening and Van Deemter and things like that we've discussed in class. And I just grabbed a couple of plots from a student a couple of years ago where they return things like this. Resolution as a function of flow rate goes through a maximum, and that's because the plate height from the Van Deemter equation goes through a minimum as we increase the flow rate. So this again really helps them, I think, make real or more real some of the ideas we discuss in class. Okay, so if you go to the website, multidlc.org, in the main simulator page, you will see this button there, Instructor Resources. And if you follow that, what we have posted there at the moment is 4 different assignments that have been contributed by different people. So one of them is from myself, 3 others from people at different institutions who have developed assignments using the simulator and are sharing them with the community. By far the most rich resource, though, in my opinion, for instructors at the moment can be found what was developed by Chuck Lucy at the University of Alberta. It can be found by going to the ASDL library website here. This is the main site. And if you search for Hplc Simulator, it will take you to this link here. And if you follow that link, this is Chuck's description of what he's developed. So he's developed assignments for getting at chromatography basics, again using the simulator. He's developed assignment for exploring reverse, the characteristics of reverse phase liquid chromatography in particular. And very importantly and very valuable, he provides a kind of instructor's manual for how to use the simulator in teaching and a solution manual for the assignments that he's developed here. So this is really a tremendous resource, really a gift from Chuck to those of us teaching using the simulator. Now just a quick sneak peek at the future. We're looking to add data for more compounds and especially different stationary phases. So these features are not live yet. We're still working on them, but if you're interested in this and you want to make comments about that to influence what we do here, please do let me know by email. But I'll just show you really quick how we imagine this is going to look. So if I go back here, so in what I showed you before, if you go to column properties, there's only one option here, and the data that supports this is based on organic solvent and water only, no buffer. So what we're working on now is pulling in data for other stationary phases and buffered mobile phases so that we can work with ionic compounds. So now in this list we have 3 different additional phases. If I choose this one, this now has data right now for only 5 compounds just to demonstrate the idea. But these data were acquired with pH 3.2 mobile phase. And we see in this case that nortriptyl and amitriptyl are actually coelute here at a long retention time. But now what we can show students is that if we go back to our column list here and choose a PFP column, that those peaks are very nicely separated and in fact in a shorter analysis time. So it really makes the point of how powerful changing column selectivity stationary phase chemistry can be for optimizing separations as well. So again, we're working on this now, and if you this is interesting to you, please let me know, and perhaps we can engage you when we get further along to have you test out some features. So with that, I just want to thank the Dreyfus Foundation for providing some support along the way for our work on this. Also, we've had a little bit of support from the National Science Foundation from a couple different grants to support things along the way. Again, this all started in my work with Pittcon, and Paul Boswell was very helpful along the way, sort of in that intermediate stage, working with it as a Java application. Chuck Lucy has really been a great partner recently in developing these instructor resources, and these are the 3 main students that have worked on the simulator over the years, including Tom Lauer, who's the sort of the current keeper of the simulator and actually started working with me as a high school student. So he's really done tremendous work. And please, if you have questions, let me know. Thanks so much.